welcome back to the channel where we discuss about material science and metallurgy course. And moving on to the topic, as we were discussing about the different transformations from liquid, and they are isomorphous, eutectic, partial eutectic, and also peritectic reaction we have seen in detail. And now we are going to discuss about these transformations that are taking place in the solid. So interestingly, the first type is in the allotropy. That means existence of two or more crystal structure at different temperatures is called allotropy. That means you can see here at this phase you have a liquid, and let's say this is the melting point, and you can see there is a change in the region, and it is something called as alpha zone, and then you have also beta zone. So you have gamma and alpha present, which is nothing but a different crystal structure altogether. And we are going to have the same type in the iron, which is also going to demonstrate different crystal structures like FCC, and then BCC, and again FCC as the temperature drops. Then this is a transformation that is also very popular in gold, copper, palladium, wherein there may be an orderly arrangement or a disorderly arrangement. So this is a transformation in the solid state as it cools from freezing temperature to room temperature. Then comes an interesting thing which is called eutectoid reaction. Now you must have remembered about eutectic reaction. So if you recall, eutectic reaction is when liquid gives rise to two new solids, and that is ending with the tick because it is having on the left hand side liquid. All the reactions which have liquid on the left hand side will end with the tick, like eutectic, peritectic, monotectic, syntectic, and so on and so forth. When it is ending with toid, like in this case, then it means that it is going to have a reaction in the solid state. That's why it is eutectoid, peritectoid, so on and so forth. So in case of eutectoid reaction, you can see on the on the solid gives rise to two new solids. Like this is the case where you can see at this point on here you have a solid gamma giving rise to alpha plus beta, that is ends of the line, and you have that happening here at this temperature and composition, and the mixture is called eutectoid mixture. So there it was called eutectic mixture, here it is called eutectoid mixture. And when it comes to peritectoid, there it was liquid plus delta gives rise to a solid, or liquid plus solid gives rise to a new solid. Here there is solid plus solid reacting to give a new solid. So you can see alpha plus beta giving rise to gamma at this particular point, and this is called peritectoid reaction. So these are the solid transformations. Okay, so now let us understand. Let's take one simple example, like isomorphous system, and try to understand how it transforms and all. So let us say, like I have to understand about the transformations which is in this phase. So what is this phase? Like A is in a single phase and above the liquidius line. So everything that is there is completely soluble. Since I said this is an isomorphous system, it is completely soluble in the liquid state as well as in solid state. So this happens to be in a single phase A. Now, if I want to know about the composition, what I'll do, I'll just drop this onto the base and read the composition straight away. Since it is single phase, complete liquid and having a composition of 50 percentage of B. That means A 50, B 50. So that is the composition of A. What about the B? Or let's say, what about E? E is also completely soluble, so single phase. So E composition is also 50A, 50B, and it is how represented. But what about anything in between? So in between, meaning just below the liquidius and inside and just above the solidius. If I take these points B, C, D, they belong to a two-phase region wherein you have both liquid and solid present. In such scenario, how are we going to calculate what is the percentage of liquid and solid present in this two-phase region? And in order to know, calculate this, we will go with a rule called liver rule. So before we go into the liver rule, let us understand the importance of this. So if I take this particular C element, how much is the portion of liquid present? How much is the portion of solid present? Is not easy to calculate straight away with this diagram. And we know already that since this is a single phase, you'll have complete liquidious liquid present. And as it reaches this liquidious line, it is the region where the beginning of transformation takes place. It starts with the formation of nuclei, then grows into dendrite, and this will be the end of solidification, above which only at the grain boundaries there is a liquid present. And just below this line, that grain boundaries are also solidified, and you'll end up getting a complete grain structure like shown in this case. Now the question is, how do we determine what is the percentage at each of these two phase region? And that's where we use a rule called liver rule. So this is liver rule. So liver rule is very simple, like how we use a liver in terms of the fulcrum at the center, and then you have a way balance on either side. In the same principle is used here. So let's say we have isomorphous system, and on the x-axis I represent the percentage of B which is varying, and on the y-axis we have temperature. Obviously this is the liquidious and this is the solidious line. And let's say I want to notate at this two-phase region, like what we discussed in the previous slide. So I want to know what is the amount of liquid and solid present. If at all I want to represent this point, need to give two variables. That is, what is the temperature and what is the composition in order to mark that point. Suppose if the temperature is here and the composition is here, then it falls into a single phase. Similarly is the case, suppose it is a composition is here and the temperature is here, it falls into a single phase. So we need to give two information, that is the temperature and the composition, which has to be inside the two-phase region. And in order to do that, let's say we apply a liver rule, and the first statement of the liver rule is to draw the horizontal line for the given temperature. So when we draw the horizontal line for the given temperature, let's say it falls here. Now this will intersect the liquidious line and the solidious line at 2 points. So you can see liquidious line is intersected here and solidious line is here. And in order to know the composition, straight away drop onto the base to read the respective composition. So when I drop onto the base, I can read that there is a composition of B10, that means A90, B10. Similarly, there is another composition called A20, B80. But what are they? Their respective composition. That means liquid composition is given here and the solid composition is given here. So this is the liquid and this is the solid. And this is the first statement of the liver rule. Second statement is to draw the composition or vertical line at the given composition. So when I draw the vertical line at the given composition to determine this two-phase region, it will divide the tie line. That means the horizontal line is also called as tie line, and this will divide the tie line into two parts. So you can see there is two-part division. It is two, not two halves, but it is two parts. So you can see this is one part and this is the other point. So the second statement of the liver rule states that when you draw a vertical line, it will divide the previously drawn tie line into two parts, and the lengths of these are inversely proportional to the amount of faces present. So when I say inversely proportional to the amounts of the line, faces present, so if I want the liquid, that is, this is the liquid here. So if I want liquid, I need to take this opposite length because they are inversely proportional, and the length, that is what we are going to determine. So this length is for the solidius and this length is for the liquidius. So when I make a simple line diagram of this, so I'll represent this as the solid and this as the liquid. And if I mark that this is M, this is N, and this is O, and I already know that this is 10, 60, and 80. So I'll write the same 10, 60, and 80. Now, so we have what are all needed, and I need, if suppose liquid, I need to take this length, And since this is the percentage of liquid we are determining, we divide this length by total length and into 100 will give the liquid percentage. And if you do 100 minus, because it is binary, you will get the solidus, or you can take this length, divide by the total length into 100 will give the solidus. So if I want this length, obviously it is 60 minus 10. So that will be this difference. And if I want this length, it is 80 minus 60, which is 20. And the total length will be 80 minus 10. So very simple. If I want percentage of liquid, then it is this MO minus NO divided by MO into 100. And solidus, it is MO minus Mn by MO into 100. So it is very simple. Like for example, if I want liquidius, I am supposed to take inversely proportional. So this length, which is coming to 50 by total length, which is coming to 80 minus 10, 70 into 100, 71.43. And the solidus will be 100 minus 71.43, or it is same as if I want a solidus, that means this length, which is 20, divided by the total length, which is 80 minus 10, 70 into 100, which is 28.57. So this is how we are supposed to calculate the liver rule for any given two-phase region. So it can be anywhere, and it can be calculated using this liver rule simply on any of the eutectic regions or isomorphous system or any peritectic or anything. So this is going to be a very important thing for determining. I hope you had a good time learning the liver rule. So see you next time. Thank you for joining.